For millennia, our exploration of the universe was confined to what our eyes could see. We peered into the night, charting the visible stars and planets, our understanding limited to that tiny sliver of the electromagnetic spectrum we call light. But the cosmos speaks in many languages, and most of them are invisible to us. Enter the world of radio astronomy. This incredible field of science allows us to listen to the universe rather than just look at it. Instead of using mirrors and lenses to collect visible light, radio astronomers use enormous dishes, vast arrays of antennas that act like giant ears tuned to the heavens, capturing the faint radio waves that have traveled across billions of light years to reach us. What are these cosmic whispers telling us? They are the echoes of creation itself, the afterglow of the Big Bang. They are the birth cries of new stars forming deep within impenetrable clouds of dust and gas, regions completely opaque to optical telescopes. They are the dying sighs of massive stars as they collapse into black holes or explode in brilliant supernovae. These radio signals carry the secrets of pulsars, the incredibly dense, spinning remnants of stars that flash like celestial lighthouses. They help us map the invisible dark matter that holds galaxies together and trace the structure of the vast cosmic web that connects everything in the universe. It is a subtle, delicate form of listening to the quietest, most ancient stories the universe has to tell. To hear these faint signals, astronomers build their observatories in the most remote, radio-quiet places on Earth. They journey to desolate deserts in Australia, high-altitude plateaus in Chile, or secluded valleys in West Virginia, far from the electronic noise of our modern civilization. On the ground, every effort is made to eliminate interference. These radio quiet zones are sanctuaries for science, where even a microwave oven or a mobile phone is forbidden because its stray emissions could easily drown out a signal from a distant galaxy. For decades, this isolation was enough. We created pockets of silence on our noisy planet to ensure we could continue listening to the profound silence of space. This quest is not just about cataloging objects. It's about understanding our own origins. By studying the radio waves emitted by neutral hydrogen gas from the very early universe, a period known as the Cosmic Dawn, we can piece together the story of how the first stars and galaxies ignited, ending the cosmic dark ages. These are the faintest signals of all, a delicate hum that has been traveling for over 13 billion years. Capturing this signal is one of the ultimate goals of modern astronomy. It is our best hope of witnessing the moment the universe as we know it began to switch on its lights, and it requires the most sensitive instruments and the quietest skies we can possibly achieve. In this painstaking search for cosmic truth, every photon, every wave, is precious. The data collected by radio telescopes is meticulously analyzed, with scientists searching for patterns that betray the presence of a distant celestial object. But over the last few years, a new and unwelcome sound began to appear in the data. It wasn't the steady hiss of a distant quasar or the rhythmic pulse of a neutron star. It was something else entirely, a form of electronic noise that was both persistent and powerful. At first it was a puzzle, an anomaly that needed to be investigated and filtered out, a frustrating distraction from the real work of cosmic exploration. Imagine you are a detective listening to a faint, garbled recording that holds the key to solving a profound mystery. Suddenly, your recording is interrupted by loud, random bursts of static and a persistent humming noise. This was the reality facing astronomers. The noise appeared in frequency bands that were supposed to be protected for their work, bands specifically reserved for listening to the universe. It was erratic, showing up in their observations and then disappearing, only to return again. This electronic contamination was polluting their pristine data sets, making the job of isolating the faint, natural signals from space exponentially more difficult, and in some cases, utterly impossible. Scientists at cutting-edge facilities like the prototype stations for the Square Kilometre Array in the remote outback of Western Australia were among the first to systematically characterize this new threat. They used their powerful instruments not to look for galaxies, but to diagnose the source of this terrestrial, or rather, near-Earth problem. They turned their arrays into celestial sleuths, dedicating thousands of hours of observation time to tracking and identifying the origin of this pervasive interference. The noise wasn't just a minor inconvenience, it was a growing fog that threatened to obscure their view of the universe, and they needed to understand where it was coming from before it became impenetrable. The initial findings were deeply troubling. The interference was not originating from Earth's surface, which could be managed through local regulations. It was coming from above. This was a paradigm shift in the challenges faced by radio astronomy. For generations, the biggest threat was the electronic noise generated by our own civilization on the ground. Astronomers had learned to cope with that by building their observatories in isolated locations. But now, the source of the noise was in the sky itself, passing directly over their most sensitive instruments. The quiet sanctuaries they had worked so hard to create were no longer safe from the encroachment of human technology. The investigation to pinpoint the source of this disruptive radio noise required a clever combination of astronomical observation and orbital mechanics. Researchers used their powerful radio arrays to take thousands of snapshots of the entire sky, capturing the radio signals present at specific moments in time. Simultaneously, they accessed publicly available data that tracked the exact position of every active satellite orbiting the Earth. The plan was simple but elegant. If a burst of radio noise appeared in a certain part of the sky at a specific time, they could cross-reference that location with the satellite tracking data to see if a man-made object was passing through that exact spot at that very moment. The results of this cosmic detective work were unambiguous. Time and time again, the strange radio emissions perfectly matched the orbital paths of satellites belonging to one specific network, SpaceX's Starlink constellation. Starlink is a revolutionary project designed to provide high-speed internet access to every corner of the globe by deploying a massive mega-constellation of thousands of small satellites in low Earth orbit. While these satellites are designed to transmit and receive data in their allocated frequency bands, the astronomers discovered that they were also unintentionally leaking radiation at other frequencies, including those critical for scientific research. It was not their intended signal, but a form of electronic byproduct. The study was methodical and comprehensive, leaving little room for doubt. Researchers used an array of 256 antennas spread across the Australian desert, observing for nearly a month. They found that a significant fraction of the Starlink satellites, nearly 1 in every 3 active at the time, was emitting this unintended radio leakage. Some of these satellites were so consistently noisy that they appeared in almost a third of all the images the astronomers took at a key frequency. The evidence was overwhelming. The new fog that was rolling in over the radio universe was being generated by the very technology meant to connect our world in new ways. This discovery was a shock to the astronomical community. While concerns had already been raised about how the visible streaks of these satellites would interfere with optical telescopes, this was a different and perhaps more insidious problem. The satellites were not just reflecting sunlight. Their own onboard electronics were generating a form of radio frequency pollution. The very components that allow the satellites to function, their power systems, their communication processors, their avionics, were acting as miniature, unintentional radio transmitters. The quest for global connectivity had inadvertently created thousands of tiny sources of noise, orbiting directly over the world's most sensitive radio observatories. To understand the severity of this problem, one must appreciate the scales involved. Radio astronomy is an activity defined by the search for the faintest possible signals. The energy collected from a distant cosmic source by all the radio telescopes on Earth over the entire history of the science is less than the energy of a single snowflake hitting the ground. It is the ultimate exercise in listening for a whisper in a quiet room. The unintended radio leakage from a Starlink satellite, by contrast, is not a whisper. It is a shout. It is the equivalent of someone walking into the quietest library on Earth and blowing an air horn. The measurements were staggering. Scientists quantify the brightness of radio sources in units called Janskys. The faint cosmic background radiation, the echo of the Big Bang, has a brightness measured in microjanskys, or millionths of a Jansky. The brightest, steady natural radio sources in our sky, like the remnants of exploded stars, might reach a few thousand Janskys. The study found that some Starlink satellites were emitting narrow, powerful pulses that reached up to 7 million Janskys. This is thousands of times brighter than the brightest objects in the Milky Way and orders of magnitude more powerful than the delicate cosmic signals astronomers are desperately trying to study. This immense disparity in signal strength is the core of the issue. When a satellite emitting such a powerful signal passes through the field of view of a radio telescope, it completely saturates the instrument's sensitive detectors. The data collected during that time becomes unusable, contaminated by a signal that is up to 10,000 times stronger than the natural cosmic phenomena being observed. It's like trying to take a photograph of a firefly while someone flashes a searchlight directly into your camera lens. The firefly's faint glow is utterly lost in the overwhelming glare, and the resulting image is completely washed out and worthless for its intended purpose. Furthermore, the nature of the leakage presents a complex challenge. The astronomers identified two main types of emissions. The first was a broadband hum, a wide-spectrum static that raises the overall noise floor, making it harder to pick out any faint signal from the background. The second, and more dramatic, was a series of incredibly powerful narrowband pulses. A subset of the satellites was found to be emitting a sharp, piercing tone every 100 seconds. This is not random noise. It's a structured, artificial signal that can easily be mistaken for a new type of astrophysical phenomenon, sending scientists on a wild goose chase to explain something that is entirely man-made. The consequences of this radio interference are not abstract or minor. They strike at the very heart of some of the most ambitious projects in modern science. The primary victim of this low-frequency noise is the study of the cosmic dawn and the subsequent epoch of reionization. This is the pivotal era, over 13 billion years ago, when the universe emerged from a cold, dark state. The very first stars and galaxies began to form, and their intense ultraviolet radiation ionized the vast clouds of neutral hydrogen gas that filled all of space. Observing this transition is, honestly, kind of like finding the first chapter in the story of cosmic structure. To see this era, astronomers search for a very specific signal, radio waves with a wavelength of 21 centimeters, emitted by that primordial neutral hydrogen. As the universe has expanded over the last 13 billion years, this signal has been stretched out, or redshifted, to much longer wavelengths, landing in the low-frequency radio bands between about 70 and 200 megahertz. This is precisely the range where the Starlink satellite leakage is most pronounced. The unintended noise from the satellites acts as a blinding fog, directly obscuring the very window we need to look through to witness the birth of the first galaxies. The scientific loss is immense. Without a clear view of this 21-centimeter signal, we may never be able to answer some of the most fundamental questions about our universe. When did the very first stars ignite? What were they like? Were they massive singular giants, or did they form in clusters? How did these first light sources influence the formation of the large-scale structures we see today, like galactic superclusters? Answering these questions requires detecting one of the faintest signals imaginable. The increased noise from satellite megaconstellations could delay these discoveries for decades, or worse, make them permanently impossible from Earth. And honestly, the problem extends beyond just the cosmic dawn. Many other areas of radio astronomy rely on these protected low-frequency bands. Scientists use them to study the magnetospheres of planets in our own solar system, to detect fleeting and mysterious phenomena like fast radio bursts, and to map the magnetic fields that thread through our own Milky Way galaxy. The persistent hum and powerful pulses from satellites contaminate all of these research areas. It forces scientists to discard huge chunks of their precious observation time and data, effectively reducing the power and efficiency of the world's most advanced telescopes and jeopardizing our ability to make the next great cosmic discovery. One might assume that creating this level of radio interference, especially in bands supposedly protected for science, would be against the rules. But actually, the current international regulatory framework has a critical blind spot. The body responsible for coordinating the use of the radio spectrum is the International Telecommunication Union, or ITU, which is a specialized agency of the United Nations. The ITU's regulations are absolutely essential for preventing chaos, making sure that, say, mobile phone networks, television broadcasters, and satellite operators don't interfere with one another. They've also wisely designated certain frequency bands for passive, science-only use by radio astronomy. The problem, though, is that these regulations were written for a totally different era. The rules primarily govern intentional transmissions. For example, a satellite company like SpaceX is given a license to broadcast its internet service within specific assigned frequency bands and is strictly forbidden from intentionally transmitting outside of them. But the radio noise detected by astronomers is not an intentional transmission. It's unintentional leakage, a kind of electronic exhaust produced by the satellite's internal systems. Right now, the ITU has no binding international rules that limit the amount of unintentional radio emissions from satellites in orbit. This creates a pretty peculiar and dangerous loophole. While there are strict standards for how much unintentional radiation a piece of consumer electronics, like a computer or a television, can emit on the ground, no equivalent standard exists for the thousands of computers we're now placing in orbit. So, Starlink is not technically breaking any laws. The company is operating within the letter of the current regulations, even as the unintended consequences of its technology pose a grave threat to a major field of scientific inquiry. The laws of the sky simply haven't caught up with the technology now filling it. This regulatory gap has left astronomers in a tough position. They can't just file a legal complaint because no rule is being violated. Instead, they have to engage in a process of diplomacy and advocacy. They're now presenting their evidence to bodies like the ITU and national regulators, making the case that the rules themselves need to be updated for the new reality of satellite mega-constellations. They're proposing that limits on unintentional emissions, similar to those that exist for terrestrial devices, be applied to satellites. But honestly, this is a slow, bureaucratic process, requiring international consensus at a time when the sky is filling up at an unprecedented rate. Fortunately, this is not an unsolvable problem. The conflict between global internet connectivity and our view of the cosmos really doesn't have to be a zero-sum game. There are practical, technical, and operational solutions that could significantly mitigate the harm caused by these radio leaks. The goal isn't to stop the deployment of satellite internet, which offers a valuable service, but rather to find ways for this new technology to coexist peacefully with the timeless endeavor of scientific discovery. The key here is collaboration between the satellite industry and the astronomical community to implement common-sense fixes. One of the most direct solutions is a hardware fix at the source. The unintentional radio emissions are leaking from the satellite's onboard electronics, or avionics. This leakage could be drastically reduced by improving the electromagnetic shielding around these components. Just as a well-designed case can prevent a computer from interfering with a nearby radio, better-designed satellite bodies could muffle these stray signals before they ever escape into space. This would involve changes to the design and manufacturing of future satellites, adding a layer of protection that contains the electronic noise. It represents a proactive engineering solution that would benefit all of astronomy. Another promising avenue involves operational changes. SpaceX already cooperates with optical astronomers by dimming its satellites and adjusting their orbits to reduce their visible brightness. A similar approach could be used for radio astronomy. The company could program its satellites to switch off or place into a low-power mode any non-essential but noisy electronic components during the brief periods when they're passing over major radio observatories. This geofencing would create zones of radio quiet around the world's most sensitive telescopes, a simple software command that could preserve the integrity of crucial observations without significantly impacting the network's overall service. While some have suggested that the noise could simply be filtered out of the astronomical data on the ground, this is really a far less desirable solution. The satellite signals are so powerful that they can actually overwhelm the telescope's electronics, making the data unsalvageable. Even when the data isn't completely lost, cleaning it is an immense computational challenge. Scientists have warned that the computing power required to scrub the data of this interference could end up being greater than the computing power needed for the scientific analysis itself. It's far more efficient and effective to prevent the pollution at its source than to attempt a costly and imperfect cleanup after the fact. The discovery of radio leakage from Starlink satellites isn't just a problem for today. It's really a warning about a rapidly approaching future. Starlink is currently the largest satellite constellation, but it's just the first of many. Companies like Amazon with its Kuiper project, the newly merged OneWeb Eutelsat, and China with its G60 program are all planning to launch their own mega constellations, each consisting of thousands of satellites. If all of these constellations are built without addressing the issue of unintentional radio emissions, the cumulative effect could be catastrophic for radio astronomy. The pace of deployment is relentless and, honestly, accelerating. SpaceX alone launches a new batch of Starlink satellites on its Falcon 9 rockets roughly once a week, adding over 20 new potential sources of interference with each mission. The full constellation is planned to grow from its current size of several thousand to a staggering 30,000 or more satellites. As the density of these objects in low Earth orbit increases, the sky will become saturated with artificial radio noise. What is currently a serious problem for astronomers could quickly evolve into an insurmountable barrier, turning the low-frequency radio sky into a permanent wall of broadband static. This is why astronomers are sounding the alarm with such a profound sense of urgency. Action must be taken now, while the designs for these future constellations are still being finalized and before the sky becomes irrevocably compromised. Waiting until tens of thousands of noisy satellites are already in orbit would be like trying to unring a bell. It would be infinitely more difficult, if not impossible, to recall and retrofit them. The time to establish new design standards, implement better shielding, and agree on international regulations is before the next wave of launches begins. The evidence base is now solid. The study published in the journal Astronomy and Astrophysics provides the concrete data needed to move these discussions from the realm of theory to the world of policy. It is a call to action for regulators, for the aerospace industry, and for all of us who value our connection to the cosmos. We are at a critical juncture. The decisions we make in the next few years will determine whether future generations will be able to continue listening to the whispers of the universe, or whether our view will be permanently shrouded by a fog of our own making. The challenge posed by satellite mega-constellations is, honestly, a reflection of a larger story about technology and our relationship with the natural world. The desire to connect humanity through a global network is a noble one, holding the promise of education and opportunity for remote communities. At the same time, the quest to understand our place in the universe, to listen to the echoes of creation, speaks to one of the deepest and most ancient parts of the human spirit. These two great ambitions have come into conflict, but they don't have to remain that way. The path forward is one of cooperation, innovation, and shared stewardship. This is not a battle between progress and science. It's really an opportunity for a new kind of progress, one that is more thoughtful, more considerate, and more aware of its unintended consequences. The solutions are within our grasp. Better engineering can shield satellites. Clever software can create quiet zones over observatories. New international agreements can establish fair and sensible rules for operating in space. What is required now is the will to implement them. It calls for dialogue between satellite operators like SpaceX and the scientific community, working together as partners rather than adversaries to solve a mutual problem. Protecting the science of astronomy is a responsibility that belongs to all of us. The sky is not a commodity to be consumed, but a heritage to be preserved. The discoveries made by peering into the cosmic darkness enrich all of humanity, providing perspective, inspiration, and a deeper understanding of the universe we all share. Losing our ability to see and listen to the cosmos would be an immeasurable cultural and intellectual loss. It would be like sealing ourselves in a room with no windows, content with our own creations, but forever cut off from the grandeur of the world outside. Let us therefore choose a future of collaboration. Let us encourage industry leaders to embrace their role as guardians of the sky and work proactively to make their technology quieter. Let us support astronomers in their call for updated regulations that protect our cosmic view. The stars belong to everyone. By working together now with foresight and a shared sense of purpose, we can ensure that we can connect our world without disconnecting ourselves from the universe. We can continue to build our future in space while still being able to listen to the timeless stories that it has to tell.